Today's lesson is about acid-base equilibrium. This is for grade 12. Okay, I'm going to make this unit as 2 or 3 parts, and this is the first part. So, first, let's remember what do we mean by equilibrium. And let's take a look at the learning outcomes for this part. First, remember the definition of equilibrium. Write the dissociation reaction of water. Write the expression of Kw and then work its units. State the factors that affect the Kw, which is the water constant, dissociation constant. Write the expression Ka, Kb and work their units. Work the values of Ka, Kb for weak acids and weak bases respectively, and calculate the value of H concentration and concentration of OH of strong acids, weak acids, and bases. Okay. The first objective is to remember what do we mean by reversible reaction. Okay. A reversible reaction is a reaction in which reactants form products and actually products reform reactants. So let's say we have A plus B and that forms C plus D. Okay, so these reactants are reacting to form the product C and D. And in the same time, C and D also react to form A and B. So instead of writing two equations, we only write one and we represent the reaction with two arrows, like these two arrows. So this means that this is a reversible reaction. A and B forms C and D, and then C and D also reform A and B. And when this happens, we say that the reaction has reached to equilibrium. But what is a dynamic equilibrium? To be specific, a dynamic equilibrium is when the forward reaction equals the rate of reverse reaction. So actually there is a reaction going, but there is no change. The concentration of reactants and products remains constant because as these two, for example here, 1 mole of A, 1 mole of B gives 1 mole of C and 1 mole of D. At the same time, it's reversed. 1 mole of D plus 1 mole of C gives 1 mole of B and 1 mole of A. So actually the concentration does not change of the products and the reactants. Okay, now let's go back a little more and remember what do we mean by acid and what do we mean by base. According to Arrhenius or Lewis Bronsted, we said or we have learned that acid is a proton donor, base is a proton acceptor. So if we apply that on water, from many different reactions that you have studied in the previous years, you have learned that water actually can work as acid and base. It can work as acid when it's reacting with base and can work as base when it's reacting with acid. So the water actually able to react as acid, which is proton donor, and also react as base, which is a proton acceptor. Okay, where in equilibrium, we can actually simplify that H2O liquid in H2O. So if you look at the reactants, actually here we have a hydronium ion. This hydronium ion, actually we can simplify it and only write H with a plus. But actually hydrogen is too small atom to be found alone, and this is the correct form. But we can write it like that anyway, it's correct. So the water actually there, it's conjugated base and acid, and this is the conjugated base. To simplify that, we can write the equation as follow. H2O can dissociate and gives a hydronium or a proton, and OH, which is hydroxyl. And at the same time, the hydroxyl react with the proton, which is hydrogen, and also gives water. Okay, now what do we mean by ionic product of water? The equation in aqueous solution, so water, when it's pure water, actually it can dissociate into a proton, hydrogen, and OH. Okay? When you studied acid and base last year, we studied something called Kc. What is Kc? Actually, this is called the equilibrium dissociation constant. And that, as we have seen, or as we have learned, that dissociation constant, we can write it using this rule. If you have a chemical reaction where A plus B gives C plus D, the small letters M, N, P, and Q, actually they are the balancing of this equation. So actually they represent the number of moles in this equation. And these small brackets, they mean the concentration. So let's use this equation, the Kc, and apply it on the reaction of water that we have used. So the equilibrium constant is always, just to remind you, Kc equal concentration of products on concentration of reactants. So if we have our equation, okay, let's put it here to remember. We have H2O, which can dissociate into hydrogen plus OH minus. Okay, so let's apply this to that equation. As we can see, the Kc, which is the equilibrium expression, dissociation of water, equals, at the denominator we have hydrogen, concentration of hydrogen multiplied into concentration of hydrogen, and divided by the concentration of reactant, which is water. Now let's rearrange. Okay, we only need that. So Kc times the concentration of water gives that. Okay, this we can refer to it as Kw. Okay, in Kw, which is the constant or dissociation constant of water, equals concentration of hydrogen times concentration of hydroxide, and actually both of them, when you multiply them, it's equal 10 to the power of minus 14. Okay, but why did we remove the concentration of water? Actually, we removed the concentration of water because the concentration of water is actually bigger than the concentration of its ions. So we assumed that the value is constant. Okay? Now let's replace, as we can see, let's replace the Kc with Kw. The concentration of water is much bigger than the concentration of ions. Now, the Kw is affected only by temperature. Before you have studied the equilibrium, and the equilibrium actually can be affected by some factors. One of them is the temperature, the concentration. Okay, now for the concentration, this shows us that the value of these two is constant, which is 10 to the power of minus 14. So that's constant. So the concentration actually does not have that effect, because if one of them is rising, then the other one is falling, and both of them will always have the value of 10 to the power of minus 14. But what about the temperature? Okay, let's write the equation once more. We have the equation here. Okay, this reaction actually is Okay, actually the reaction of water is an endothermic reaction. Endothermic reaction. So as for the endothermic reaction, try to remember from that previous study. Actually, the endothermic reaction, if you want to increase the yield or increase the forward reaction, actually you raise the temperature. So if you raise the temperature, the reaction will go forward. If you decrease the temperature, the reaction will go at reverse. So now the temperature of only pure water, of course, according to Le Chatelier principle, can predict change. The dissociation of water is an endothermic reaction. So by the increase of temperature would push the reaction to the right side, making the concentration of hydrogen more than the concentration of H2O. And if you decrease the temperature, actually you will lower the pH, which you will increase the pH because you will lower the concentration of hydrogen. Again, if you increase the temperature, the reaction will go forward, making the concentration of hydrogen more. And if you make the concentration of hydrogen more, this lowers the pH. So now you have learned that the only thing that can affect the dissociation constant of water is the temperature according to Le Chatelier principle. The concentration does not affect much because actually the value is constant, which is 10 to the power of minus 14. Now, the unit of Kw. Okay, you know that the unit of any concentration equals any concentration. The unit is mole diameter cube. I don't know what's wrong. Okay, mole diameter cube minus 3. Something is wrong. Mole. Okay, so it's mole diameter cube minus 3. So mole times mole, so it's mole square diameter cube minus 3, diameter minus 3, so it's diameter minus 6. Okay, now using the Kw, we can calculate the concentration of hydrogen or hydroxide because we know that both of them are constant. Okay, using the ionic product of water. So Kw, actually we can define it as the equilibrium constant for ionization of water. Hydrogen ion concentration of pure water can then be found for each molecule of water that ionizes. One hydrogen ion and one hydroxide ion are produced. Okay,